All right, so one of the things I really want you to concentrate on is the use of Ohm's law to solve all your problems. And again, we want to make sure that we're just not solving the number, but that we are literally looking at the problem, writing down your equation, and then using the substitution method, and then following through and showing each step all the way through. That way you're catching any problems that you have. Then, as we've talked about in class already, that while there's one method for solving some of this stuff, there's typically another method in regards to using the power formula for doing some of our stuff. So we're going to concentrate just on Ohm's law right now and just make sure that we get our numbers correct, and then we'll go from there. So such that we know that in Ohm's law, we know that the voltage is equal to the current times that resistance. And that's absolutely critical in everything that we do, in that the voltage, the potential, is equal to the flow times by that resistance to the flow. All right? We know that in Ohm's law that the current is equal to the voltage, the potential, over the resistance, and that the resistance is equal to the voltage divided by the current. Now, I am using E again for representing the voltage potential. Remember that we go back and forth on that. Sometimes you'll see V, sometimes you'll see E, but always whenever we're referring to volts as in the unit of voltage, we'll use V for volts, like 10 volts. Now, if I've got a potential, let's just show the battery here, and a real simple one would be that I have a battery BT1, and let's say it's 12 volts, and out here I have resistor 1, and it is let's say 1 k ohm, okay, 1 k ohm, or 1,000 ohms. Then I want to know what the current is. So what is I? What is it? And again, all we're going to do is we're going to go over here, figure out what are we solving for, use the formula, and continue on. So in this case, we are going to use that the current is equal to the voltage divided by the resistance. Go ahead and substitute in. 12 volts is divided by 1 k ohm. And in this case, we're going to see that we are at 12 milliamps, right? I'm going to underline that, making sure it's well seen, 12 milliamps. And that means that anywhere in this circuit, this is a series circuit, there is one path all the way around, it's a series circuit, that there's 12 milliamps here, that there's 12 milliamps here, there's 12 milliamps here, and there's actually 12 milliamps going through that battery, or actually recombining all the way through. Now, this is not, they don't build upon each other. This is the same 12 milliamps. It's just wherever I measure, I'm going to see that 12 milliamps, all right? Again, if I want to, there's some other stuff that we'll talk about in the near future in regards to using multiple resistors to do what we want to do. But that's in the next video or two, right? If I had, in this case, 5 volts, do you see there? And I had 1 amp of current, right? 1 amp. And again, that current is throughout this whole circuit. And if I wanted to figure out what the amount of resistance I needed there, the amount of resistance that is producing that 1 amp or restricted to 1 amp, then I would say that resistance is equal to the voltage divided by the current. So R is equal to E over I. And then I'd substitute in 5 volts, 1 amp, and I'd see that was 5 ohms. Okay. So I put a 5 ohm resistor out here, I would have 1 amp of flow. As we spoke of in class, though, one of the main problems with this isn't the fact of that we have 1 amp. 1 amp is a lot. Okay, for us, it's a lot. But sizing this resistor is important for us because 1 amp, 5 ohms, as we saw in this overall scheme of things, that the power is equal to I squared R, as we talked about in class earlier. And therefore, the power dissipation from this is going to be 1 amp squared, so it's 1 squared times 5, which is equal to 1 times 5, which is 5 watts. Now, 5 watts for that little resistor is quite a bit, so do not go out there and just buy and get a 1/4 ohm resistor and pop in there. The moment you do that and you put that in there, it's going to get very hot very quickly and probably burn up within just a second or two. So as long as the power supply can handle that much current. 5 watts needs to be a pretty good sized resistor, and as we spoke again also, that this 5 watts is what it's going to dissipate. So that means that if that's what it's going to dissipate, we need to make sure the resistor can actually be a little bit more than that. Again, we're looking at 80% of what we should have in there. If we can't find like a 7.5 watt, which would be a little bit overkill for it, but if we could find a 7.5 watt, we'd have to probably go with a 10 watt resistor, which is pretty common for 5 ohms. So a 10 watt resistor, more than cover it, it would stay very, very cool throughout its life, which is what we want. The more it gets hot, the faster it's literally going to burn up afterwards. Right. Now, if we are looking at how much potential, again, the voltage, how much voltage are we actually needing to say I have a 1K ohm resistor and I only can use 1 milliamp. I only want to use 1 milliamp of current. What's the actual voltage that I need to have to make that work? Well, voltage is going to be equal to the current times that resistance. Substitute in 1 milliamp times 1K ohm, and that's going to be equal to 1 volt. Now, quickly, this is -3, this is to the +3. 1 to the -3, 1 times 10 to the +3. Going to leave us with 1 volt. So if I had 1 volt up here for the battery, I would have 1 milliamp of current and 1K ohm. On our current meters, it's going to be kind of hard to measure that, just simply because of the scale. But we can do it. It'll be down in that 1 milliamp range on the scale of 25, but we can definitely do it. To measure these, this is what's critical that we need to know. And as we go to measure these, if I want to measure this 1 milliamp, I have to turn off the power supply, open up this line. If I've got 2 wires in there, I'll show this in another video hopefully. I will take my ammeter, take the more positive side, hook it towards the more positive side of the battery. Take the more negative side, hook it to the more negative side of the battery, and put it on the 500 milliamp scale. Now that 1 milliamp isn't going to deflect very far. I'll turn on the power supply. I'll see that it hasn't deflected very much, so I'll shut it down, turn it off, change it to the 100 milliamp scale or the 50 milliamp scale, depending upon the ammeter that I'm using, and then turn it on again. Look at the needle deflect a little bit better, but not as much. And then I'm going to put it on the 25 milliamp scale, which is going to give me the best deflection for 1 milliamp. It's going to deflect a little bit. I'll make my measurement. I'm fine. At that point, I'll shut off the power supply. And to prove to myself that this is the current is here, but also up here, because this is just another line, I'm going to open it up here again, remove it from here, connect that back up, and put the ammeter here. And as you can see, the negative side will go on this one here, because towards more negative, and the more positive side one will go here. Once again, we'll start off with the 500 milliamp, move it over to the 500 milliamp, turn on the power supply. From the standby, you'll see the ammeter move. Shut it down, move it over to the 100 or 50 ohm one, turn on the power supply, you'll see it move better, a little bit further, and then shut it down, move it to the 25, turn it back on, you'll get the best deflection that you'll get. Again, while we have taken time to start with the 500 and then the 150 and then down to 25, that's just to verify that we don't have a 1 ohm resistor in there or a 10 ohm resistor in there, but we actually have a 10K ohm resistor. We have already determined how much we should see, but we're just trying to protect this piece of equipment now from any type of failure. Right? So using Ohm's law, just remember that whenever we report something, we're going to be in the milli, the micro, the nano, the pico range, typically for current. Very few times will we actually be in the amp range, or more specifically, we'll probably never see the kiloamps, because that's just way more than what we'll ever use. We're down to these lower ranges here. When we're dealing with voltages, we'll see voltages anywhere from the microvolts all the way up. And again, kilovolts and megavolts, won't work with those personally, not in classes, but in voltages, millivolts and microvolts will definitely be in there. And as far as resistances, we're going to see resistances in the range of ohms all the way up to megohms, so kiloohms and megohms. There are some instances where you'll see milliohms, but that's very few, and they're typically jumper wires.